Always good to have a think about structure and bonding for any group that we bring in. So here is a standard carbonyl compound, and you can see that that carbon has got 3 groups attached to it, 3 groups of electrons, and so it's trigonal planar. Okay, and you would expect in trigonal planar for the angles to be 120 degrees. However, those of you who think a little bit further than this will say, well, we've got a carbon-oxygen double bond here, and that's a pretty short, strong bond, lots of electrons there, and then carbon, whatever's, single bonds. And of course, double bonds have 4 electrons, single bonds have 2 electrons, so as we learned back in VSEPR, double bonds are more repulsive than single bonds. So thus, for example, if we just take formaldehyde or methanol here, then the angles in this are the hydrogen-carbon-hydrogen angles, a little bit smaller than 120. The oxygen-carbon-hydrogen angles are bigger than 120 because this double bond is more repulsive than the single bond, so pushes them away from itself more than they can push away from each other. Same idea goes when we go to acetone, which is the simplest symmetric ketone. Okay, you've got angle, carbon, carbon, carbon angle, smaller than 120 there because the double bond is pushing these away more. It's rather emphasized if we just think about ethanol here, right? 1, 2 carbons, and it's an aldehyde here, because now we've got the carbon-oxygen double bond pushing away a methyl group here, pushing away a hydrogen there, and so we see even more distortion and some quite significant asymmetry here, because the oxygen carbon to carbon angle, because methyl is bigger than hydrogen, bigger than the oxygen carbon hydrogen angle here, which is more than 120. This angle bigger than it is here, but not ridiculously that much different for it. But the real distortion here is what's happening associated with the carbon oxygen double bond. So some nice fun and games associated just with the structure. Now, the bonding is, of course, rather fun. Here is the carbonyl group, looked at it from the side, so that we can see those p orbitals that are sticking up perpendicular to the carbon-carbon sigma bond. And, of course, this should not be any shock to you, because those p orbitals that are sticking up perpendicular, of course, will come together to make a pi bond, just like we saw with a carbon-carbon double bond when we were talking about bonding in the alkenes. Unlike, however, the carbon-carbon double bond, oxygen is of course much more electronegative than carbon is. So that means that that pi cloud, as well as the sigma bond, are going to be polarized, right? The electrons are going to be more towards the oxygen, the more electronegative oxygen, than they are to the carbon. Now this means that in the carbonyl group, the carbon is slightly positive and the oxygen is slightly negative. And indeed, there are those who would even draw the resonance structure with the pi electrons that are so polarized towards the oxygen going the whole hog and completely being on the oxygen, thus giving us this Zwitter ion type of structure here, carbon positive, oxygen negative. Now, of course, the reality is somewhere in between for these normal compounds. Definitely not an equal sharing of the electrons like we have here, a polarized sharing, it's a polar bond, but it's not going to be fully ionic like this. However, if we think about it, knowing therefore that this oxygen is quite a bit slightly negative and the carbon is significantly slightly positive, this gives us 2 nice reactive sites for our carbon-oxygen double bond. We have a slightly positive carbon, which is going to be very attractive to nucleophiles, things that like positives, okay? And as we will see a bit later on, the significant chemistry of the carbon-oxygen double bond is associated with nucleophilic attack on this slightly positive carbon. However, we must not forget, and we will see this in at least one place in the module, that this oxygen up here sticking out there from the one side of the molecule, quite a bit delta negative, so it can attract electrophiles to it. Electrophiles can come up, they're like those slightly negatives, get some electron density from the oxygen and do a reaction that way. So carbonyl groups really cool in that they have 2 significant reactive sites that do things differently. Slightly positive carbon that will attract nucleophiles, slightly negative oxygen that will attract electrophiles.